So for many years, discoveries in chemistry were made quite literally by accident. Alchemists, the forefathers of modern chemistry, randomly mixed chemicals together and literally prayed for a discovery that would make their fame and fortune. In physics, the ancient Greek philosophers used math and logic to predict and theorize outcomes. Later, Sir Isaac Newton would predict the orbits of planets, but never travel into outer space to do so. A Swiss-born Russian chemist laid the foundations of theoretical chemistry by formulating a law which now bears his name and is called Hess's law. Hess showed that the total energy evolved or absorbed by a particular chemical reaction is a constant no matter what steps are used to achieve it. As an analogy, you can imagine climbing a mountain by several different paths, but your change in potential energy will always be the same. Likewise, Hess's law allows you to design your own reaction using known reactions to assemble it. So let's take a look at how this would play out. In this example, we see sulfuric acid is being broken down into sulfur trioxide and steam. We're given three reactions here, and we want to show that these three reactions can be added algebraically to equal the reaction that we're given. So take a look at the first reaction that is shown. In this example, sulfuric acid is on the product side of the reaction that we're given, and we need it on the reactant side for the reaction that we're trying to build here. So I'm going to flip this reaction, and we're turning, in that case, an exothermic reaction into an endothermic reaction, which means that we need to change the sign on the enthalpy value, or the heat value that's shown on the right. So we're changing that to a positive sign. In the second reaction, we see sulfur trioxide, which is exactly in the spot we need it. So we're going to leave that alone, as well as the enthalpy value that we're given for this too. Looking at the third reaction, which is basically just turning water liquid into steam, or boiling it, you can see that everything is set and in the right spot for us in this case as well. So we're going to leave that alone and leave the heat value the same as 44 kilojoules. Now, algebraically, we want to show that these three steps add up to equal the reaction that we're given to begin with here. And so we're going to cross out things that appear on opposite sides of the equation. So the hydrogen sulfide gas goes away, the oxygens go away as well, and so does the liquid water. And now if we add these three equations up algebraically, we should get the reaction that is shown above. And if that's the case, then we can also add up all the enthalpy values as well, the heat values, and just paying attention to the positive and negative signs, we get that this reaction is going to be a positive 72.5 kilojoules. So it's an endothermic reaction. Alright, so we'll take a look at another example, a little bit more complex. In this case, we have some carbon disulfide, reacts with oxygen gas and produces carbon dioxide and some sulfur dioxide. We have three reactions that we're going to try to show equal that. First of all, in the first reaction, we have carbon dioxide, which is in the correct spot as a product. So I'm going to leave that one entirely alone and leave the enthalpy value just the way it is. In the second one, we have sulfur dioxide in the correct spot, but in our reaction we need two of those. So I'm going to multiply the reaction given times 2. If we multiply the reaction times 2, we need to multiply the enthalpy value as well. Because if you look at the units on this, it's kilojoules per mole, and now we're producing 2 moles of sulfur dioxide. So again, that's why we're multiplying that one times 2. In the third reaction here, we have some carbon disulfide, which appears as a product in the reaction that we're given, and it's a reactant in the one that we're trying to create. So again, we're going to flip that one and change the sign of the enthalpy value, just like we did in the previous example. Now we're going to cross out things that appear on opposite sides. The carbons go away, and the sulfurs go away. And now if we add this all together, we get the reaction that we were trying to get, and it all works out nicely. add up all of your enthalpy values, again being aware of your positives and negative signs, and this one turns out to be exothermic, and negative 1075 is the number of kilojoules you would get from this particular reaction. Alright, so those are a couple of examples, relatively simple examples of Hess's law. They get more complex, but the basic principles are exactly the same. I hope that's helpful to you. If you want to get a little bit more creative, you can kind of peruse through the charts of thermodynamic values, and you might be able to create your own reactions by yourself and see what you come up with, and maybe you'll come up with some important discovery. All right.